All right, so we're going to continue on with chapter 3 today, starting with percent composition of compounds. So this is a way of describing molecules and compounds by comparing masses. So basically the mass of each component of a molecule, each component of a compound compared with its total mass. So percentage-wise, how much of a compound is one element or another? I gave you kind of a little flow chart of how to solve these, but the best thing to do is just kind of jump in here and we'll look at here we have a compound. This is going to be a crystalline compound. So this was one of the first superconductors. You have Y, Ba2Cu3O7. Y is yttrium, however you want to say it. Ba is barium, Cu is copper, O is oxygen. So let's see. Calculate the percent composition by mass of this material. So we really want to know percent composition of each element in the compound. Okay. So okay, so that's what we're trying to find. Let's look at the periodic table and figure out the molar masses of each one of these elements. All right, so these are the things we know. So then we need to say, okay, we have to compare each one of these to the overall compound. So we need the molar mass of the entire compound. All right, so that's going to be Y, Ba2, Cu3O7. That's going to be 1 yttrium plus 2 bariums plus 3 coppers plus 7 oxygens. And when we add all this up, okay, now that we have this, we can start calculating the percentage of each one of these compounds. Okay, so, or each one of these elements. Percentage of yttrium. That is going to be, you only have one of those in the compound, over the total mass. Okay, and so that's going to end up being 88.91. This is going to give you 13.34% yttrium. Let's see, we'll do barium next. We're just going to go down left to right. Okay, but look at the chemical formula. There's 2 bariums in there. So in the percentage, We need both of those. All right, that's 2 times 1, 37.33. That's going to equal about 41.223%. We're keeping in significant figures. We'll do copper next. In the formula, there are 3 coppers. Three, and we see copper is 63.55. That's going to make copper about 28.61%. And we do this calculation one more time for oxygen. And you should be able to set this up by now. So there's 7 oxygens. Once you put in the number for oxygen, the molar mass for oxygen, which is 16, you'll get about 16.81%. So this is what we mean by percent composition. And it's really, you think of it as percent by mass, because you notice we were using molar masses to calculate this. Okay, now determining the formula of a compound. So compounds, they have molecular formulas. We've been looking at those. They also have empirical formulas, which is going to be the lowest whole number ratio of atoms in a compound. So if you see here, we have C6H12O6. You notice that we can divide through by 6 and get CH2O. And so the CH2O is your empirical formula because I've reduced the subscripts down to their lowest whole numbers. You have to be careful because sometimes the molecular formula is the empirical formula. If you look at the amino acid glutamine, you see you have C5H10N2O3. 5, 10, 2, and 3, they're not really going to have a common multiple. You're not going to be able to divide through and get whole numbers. So C5H10N2O3 is both the molecular and the empirical formula. So that'll happen sometimes. But let's say we have an amino acid made out of carbon, hydrogen, nitrogen, oxygen. Those A, B, C, D subscripts are different numbers. We don't really know what they are. And we combust this. And so what we do is we combust this amino acid. Okay. And so let's remember what a combustion is. We don't know what A, B, C, and D are. A combustion, we have to combine with oxygen gas. Now, for the hydrogen, carbon, and oxygen portions of this molecule, remember your hydrocarbons, you're always going to get CO2 and water. In this case, we went with a combustion that also is going to yield nitrogen gas to take care of the nitrogen portion of the amino acid. So if you combust 10 grams of this amino acid with 18.6 grams of oxygen, you find that you get 18.06 grams of CO2, 8.63 grams of H2O, and 1.92 grams of N2. Find the formula of the amino acid using mass percentages. So we'll do that. We'll go all the way there in our first example. I wanted to show you how to deal with, so this would be like you combust this in a lab and you collect these masses of your various products. And so the way you find your formulas is you're going to start with the empirical formula. And so what you need for the empirical formula are the percentages of each atom. So your composition percentages. And so you have to use your data to find that. So what I want to do is I want to walk you through carbon and oxygen and show you, well, how do I find out the percent composition of the various atoms or the various elements in this amino acid so that I can then proceed to find the empirical and molecular formula. Okay, so if I look at this, I have carbon in there, I have carbon in there. So however much carbon exists in my, so you see I only have carbon in one of my products. So that tells me however much carbon exists in the amino acid, all of it has to go into CO2. Okay, so the first thing I'm going to want is I'm going to want my molar mass of CO2 because I want to find the mass of carbon in CO2. Okay, one carbon plus two oxygens. That is going to be 12.01 grams per mole. And again, I'm getting these off the periodic table. Plus two. Oxygen is 16 grams per mole. And when I add this up, I get 44.01 grams per mole. That's probably a molar mass you should commit to memory because you're going to use CO2 for a lot of stuff. So how much mass, let's see, mass of carbon in CO2? Because see, I have a measured product. If I know the mass of carbon in my measured CO2, I know that that's the same amount of mass of carbon that came from my original amino acid since all of it had to go into CO2. Okay, well, how much CO2 did I get? I got 18.06 grams. Okay, so we're just going to start with what we have. We're going to start going through. Now, remember, in a lot of these calculations, I'm going to be comparing moles to moles because if you look at CO2, so look here, for every 1 mole of CO2, no, I'm going to get 2 moles of oxygen. Darn it, that's not what I wanted. Well, we can go ahead and do that. 2 moles of oxygen and 1 mole of carbon. You can see that in the formula. I have 1 mole of carbon and 2 moles of oxygen for every 1 mole of carbon dioxide. We're going to use that. I want you to start thinking about that, making sure you understand how that works. Okay, so the molar mass of CO2, we're going to divide by it to cancel out the units of grams. Okay, so grams is gone. All right. Now, I know in CO2, because I'm trying to find just carbon, in 1 mole of CO2, I have 1 mole of carbon. And so that's going to moles of CO2, moles of CO2. Those are gone. Those divide out. Now, 1 mole of carbon, I look at the periodic table, is 12.01 grams of carbon. And so then what I do is I see that moles of carbon cancels out moles of carbon. I multiply across the top and divide by the bottom. 18.06 times 12.01 divided by 44.01, I get 4.928 grams of carbon in my CO2. Take some time to look at what I just did there. Make sure you understand the step-by-step process. Make sure you understand how I get 1 mole of carbon and 2 moles of oxygen from every mole of CO2. And know that if I have a mass of a compound, I'm going to have to translate it to moles in order to make these comparisons, because that's how stoichiometry works. Stoichiometry is comparing molar amounts. Okay, now that I know I have 4.928 grams of carbon, I know that that's the same amount of carbon I had in my original amino acid. So I can find my percentage of carbon in my amino acid. Okay. Because I'm told I had 10 total grams of that, and in there was 4.928 grams of carbon. Okay. So, and that makes sense because I can't produce any more carbon than what is in that 10 gram sample. So if I had a 15-gram sample, uh, I would have more carbon. If I had a 20-gram sample, I would have double this mass of carbon produced in the form of CO2. So remember our percentages. We're going to do our 4.928 grams of carbon divided by the total mass of the amino acid times 100. And that's going to give us 49.3% carbon. And we can use this percentage and others to find the empirical formula. But I wanted to make sure we took a moment to cover oxygen. Okay, so if you look, we have, so we're told we use 18.60 grams of oxygen. That's that right there in the combustion. But look at our products. We have CO2, we have H2O. We have two sources of oxygen in our products. We have to take that into account. So I need the mass of oxygen in H2O. I need the mass of oxygen in CO2. Okay, so I know I need the molar mass of H2O. It's two hydrogens and plus an oxygen. It's 2 times 1.01. It's the molar mass of hydrogen plus 16. That's the molar mass of oxygen. You're going to get 18.02 grams per mole for water. Another good one to commit to memory. We already have the molar mass of CO2. So we'll use that in a second. Okay, so I was told that I collected 8.63 grams of water. Okay. Stoichiometry does moles to moles comparison. So I need to change this into moles. I'm going to divide by the molar mass. Okay, and you notice grams cancels out grams. Now I have moles of H2O. And if I look, so if I have 1 mole of H2O, that's going to give me 2 moles of hydrogen and 1 mole of oxygen. So you notice your 2 goes to there, your 1 goes to there. So I'm looking for oxygen in H2O. Well, I know that for 1 mole of water, oh, I'm looking for oxygen. I keep going backwards. I have 1 mole of oxygen. Okay, so that is going to moles of H2O. Moles of H2O divides out. And then I say I want grams of oxygen. So that's going to be grams of oxygen per mole. And then, of course, moles of oxygen cancels out. All right, so I'm going to multiply this up. This is going to give me 7.66 grams of oxygen. And I get that from water. Okay, I also need to know the amount of oxygen that's in the CO2. Because I have to account for all of the oxygen in my products. And then I have to look at that in terms of my reactants. Okay, so remember we have 18.06 grams of CO2. All right, now I need to turn this into moles. 44.01 grams per mole of CO2. Grams cancels out. Now in CO2, this time you see for every 1 mole CO2, there's 2 moles of oxygen. And again, that's just because of that subscript 2 on the oxygen. So for you think of it as molecules too. For every 1 molecule of CO2, I get 2 oxygen atoms. So same idea. Okay, and I'll cross the rest of these out in a minute. And then, of course, my mass of oxygen, and I'm going to need to multiply by the molar mass of oxygen. So you see moles of CO2 cancels out, moles of oxygen cancels out, and I'm left with my grams of oxygen. When I calculate this, it's going to give me 13.13 grams of oxygen. So in my products, from my products, I need my total oxygen. So that's going to be 7.66 grams from my water, plus 13.13 grams from CO2, which is going to give me 20.79 grams of oxygen in my products. Now, that oxygen comes from both the O2 and the amino acid. Okay, great. How do I know how much oxygen comes from the amino acid? Because I don't know my subscripts of my amino acid. I don't know that yet. Well, I know that 18.6 grams of it comes from the O2. All right. So oxygen from my amino acid, I'm going to take my 20.79 grams of total oxygen in my products, and I'm going to subtract off the 18.6 grams that I used in the combustion. That means that 2.19 grams of oxygen comes from the amino acid. So now that I know the mass of oxygen in the amino acid, I can do my percentage. Okay, again, I'm going to take the mass of the element that I'm looking at divided by the total mass of the amino acid times 100, and that is going to give me 21.9%. 21.9% oxygen for the amino acid. Now, I can keep doing this, and I could go through and I could get nitrogen, I could get hydrogen. The point is, I'm using experimental data to figure out mass percentages. This percent composition then is going to lead you into being able to find the formulas. Okay, so now let's look at how to do that. All righty, so uh, we're going to find the empirical formula. Remember, that's our lowest whole number ratio, our lowest whole number stoichiometry within a molecule. But then once we know the empirical formula, we're also going to be able to find the actual molecular formula of our compound. So here, again, we're looking at another amino acid. Maybe we can figure out what it is. Uh, the way that we know that our amino acid has an actual molar mass of 146.19 grams per mole. And let's say we went through that whole process of finding our empirical formula. I want you to see this first before we do that step so that we can put it all together at the same time. So let's say we went through the entire step of finding our empirical formula, and we found that it's C3H7NO. How do we find the molecular formula? Well, what we need is a whole number multiplier that we will multiply every single subscript in the empirical formula. So something times 3, something times 7, times 1, times 1, and it will give us the subscripts for the molecular formula. We get this by taking the ratio of the molar mass of the empirical formula against the actual molar mass. Now, again, keep in mind, I'm going to show you this, and then we're going to take our percent compositions and then this process right here and put them together as a whole to step through empirical formula to molecular formula. And we're going to do that by we'll have to end up making an assumption in this process, and I'll show you what that is in the next step. So yeah, let's just finish this so you know how this part of the process works. Okay, so what we need is a molar mass for our empirical formula. Okay, so what is this going to equal? That's going to be 3 carbons plus 7 hydrogens plus nitrogen plus oxygen. That's going to be 3 times 12.01 molar mass of carbon, 7 times 1.01 molar mass of hydrogen, plus 14.01 molar mass of nitrogen, plus 16.0 molar mass of oxygen. When I add this up, I'm going to get 73.11 grams per mole for my empirical formula. But I know that the actual molar mass is 146.19. So the ratio So that's going to be our actual or empirical times 100. Nope, 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 never mind. It's not a percentage. So what we're going to do now is we're going to take our 146.19 grams per mole over the 73.11 grams per mole we just calculated, and you're going to get numbers a lot like this. So 1.9996. When you get a number that's that close to a whole number, what we do is we round it to the nearest whole number. Now that 2 is our multiplier. So we'll take our empirical formula, C3H7NO. And now with this 2, that's going to be C 3 times 2, H 7 times 2, N. And of course, if you don't see a subscript, remember these are always ones. And so it's going to be 1 times 2. And the oxygen will be 1 times 2. This is going to give us C6, H14 into O2. That's the molecular formula. And so that's what we mean by a multiplier that's going to adjust all of the subscripts. Okay, and if you were looking, this is lysine. Okay, so now I showed you how I told you about percent composition. I've showed you how to find the molecular formula from the empirical formula. So let's put it all together. You'll learn the last step of this process, how to use the percent composition to find the empirical formula. I wanted to show you some data analysis, how to find percent compositions, and then show you that last little part because it's the easier part. And so now we'll put it all together. And you see here, we have a compound made up of phosphorus, nitrogen, and chlorine. And it's 26.7% phosphorus, 12.1% nitrogen, and 61.2% chlorine. It has an actual molar mass of 580 grams per mole. Okay, so we want to find the empirical and the molecular formula. Okay, so a couple things that we know. Let's see, phosphorus. I look at the periodic table, that's 30.97 grams per mole. Nitrogen is 14.01 grams per mole. Chlorine is 35.45 grams per mole. And then my actual molar mass, which if we compare, that's going to be this number right here. My actual is that 580. So these are knowns that are going to help me solve the problem. Okay, now here's the key to solving this, to getting from percent compositions to empirical formula. You're going to assume 100 grams of your compound. So what that means is just as all these percentages, so your compound is made of phosphorus, nitrogen, and chlorine. So all the percentages have to add up to 100%. So if the percentages add up to 100, that means if I just assume 100 grams, these percentages become masses. 26.7 grams of phosphorus, 12.1 grams of nitrogen, and 61.2 grams of chlorine. And as they add up to 100% when they're percentages, they add up to 100 grams when they're grams. So that's why we make this assumption. Because I can say that I can have any mass of my compound I want. So I'm saying I have 100 grams of it. So now, the next thing you're going to need is moles of your of each one of these compounds or each one of these atoms. All right. Moles of phosphorus. I have 26.7 grams of phosphorus. Phosphorus is 30.97 grams per mole. I divide by the molar mass to cancel out grams. And for phosphorus, I get 0.862 moles of phosphorus. All right. Moles of nitrogen. So I have 12.1 grams of nitrogen. The periodic table shows us that nitrogen is 14.01 grams per mole. Grams cancels out. And I end up with 0.864 moles of nitrogen. All right, now we'll do the same thing for chlorine. All right, so I start out with 61.2 grams of chlorine, and chlorine is 35.45 grams per mole. Grams cancels out, and I get 1.73 moles of chlorine. Now, the reason I can do this, the reason I can assume 100 grams, is if I have more of my original compound, I'll have more of these atoms. If I have less of my original compound, I'll have less moles of these atoms. But the thing is the ratios between them will always stay the same. So I can assume any amount of my compound that I need to. Now, now I know all of my atoms in my compound in moles. Okay, now what I do is I'm going to take ratios of these and I'm going to use the smallest number. I always want to use the smallest number to create ratios. And these are going to give me numbers that will be the subscripts of my empirical formula. So the easy one, you saw that phosphorus was the smallest. So I'm going to do a ratio of phosphorus to phosphorus. That's going to be 0.862 to 0.862. When I divide that, I get 1. The next ratio, nitrogen to phosphorus. That's going to be 0.864 over 0.862. That's going to equal 1.002, which is very, very close to 1. So we round to 1. Our last ratio is going to be chlorine to phosphorus. And we only need these 3. We don't have to ratio chlorine to nitrogen. We're going to ratio every atom to the atom that has the lowest number of moles. Chlorine is going to be 1.73 to 0.862, which is going to give us 2.007, which is very close to 2. And again, the reason this second step, we find moles, is remember those subscripts on your molecule are stoichiometry. And stoichiometry is molar ratios. And so that's what we're doing. We found moles, and now we're doing molar ratios. So now that I find that phosphorus is 1, nitrogen is 1, and chlorine is 2, that means that my empirical formula is PnCl2. Now take a moment to review this first process, because now going from here to the molecular formula is what we just did earlier. So that means I need my molar mass. It's phosphorus plus nitrogen plus 2 chlorines, 30.97 plus 14.01 plus 2 times 35.45. And that's going to give me 115.88 as my molar mass for my empirical formula. And now I'm going to do my ratio of my actual to my empirical. So remember, my actual is the 580. 580 to 115.88. That's going to give me 5.005 or about 5. And so this 5, just as we did above, becomes the multiplier of all of my subscripts. So now that means that my empirical formula, I'm going to have P, so 1 times 5, nitrogen, 1 times 5, chlorine, 2 times 5, It's going to give me a molecular formula of P5N5 Cl10. Okay, so let's do another one real quick. Oh, where's that start? Okay. So maleic acid is an organic compound composed of 41.39% carbon, 3.47% hydrogen, and the rest is oxygen. If 0.129 moles of maleic acid has a mass of 15.0 grams, what are the empirical and molecular formulas of maleic acid? Okay, so you notice that we have a couple of our mass percentages. We don't have oxygen. Okay, so the first thing I'm going to do is, okay, let's say empirical formula, molecular formula. That's what they're looking for. I'm assuming 100 grams of maleic acid. I look at the periodic table, carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. Oxygen is 16 grams per mole. And now I say, well, let's assume my 100 grams. That means I have 41.39 grams of carbon. I have 3.47 grams of hydrogen, and I need to know how many grams of oxygen I have. Well, I know that all of these have to add up to 100. So my grams of oxygen, that's going to be 100 minus 41.39 minus 3.47 equals 55.14 grams of oxygen. So yeah, I'm just going to take the amount of carbon and amount of hydrogen, subtract it off 100, and that gives me my oxygen. So once again, because I need these in moles because I need to make comparisons by molar ratios. Moles of carbon, 41.39 grams of carbon. Carbon is 12.01 grams per mole, so I'm going to divide by molar mass. That's going to cancel out grams of carbon. That's going to give me 3.446 moles of carbon. Okay, moles of hydrogen. Moles of hydrogen, that's going to be 3.47 grams of hydrogen. Hydrogen is 1.01 grams per mole. That's going to cancel out grams of hydrogen, and this is going to then multiply out to be 3.440 moles of hydrogen. And my moles of oxygen. Well, I found that I have 55.14 grams of oxygen. Oxygen is 16.0 grams per mole. I cancel out grams of oxygen, and I'm going to multiply, well, 55.14 divided by 16.0 is going to give me 3.446 moles of oxygen. Now, these are all very close, but your 3.440 is your lowest number. So that's the one I'm going to use to make all my ratios. Okay, so hydrogen to hydrogen. Three 3.440 to 3.440. That's going to give us 1. All right. Carbon to hydrogen. That's going to be 3.446 to 3.440. That's going to equal 1.002 or about 1. And you should already know that the oxygen to hydrogen ratio is the same. So I get subscripts of 1 for my entire empirical formula. Okay, so that's going to be CHO. And they each have a subscript of 1. Okay, so for my molecular formula, well, we need a couple of things. We need the molar mass of the actual compound, and we need the molar mass of our empirical formula. It's going to be carbon plus hydrogen plus oxygen. 1, 1.01 for hydrogen, plus 16 for oxygen. That is going to give us a molar mass of 29.02 grams per mole. Now, how do we find the molar mass of the actual compound? Well, okay, so this is where we go back to the definition of molar mass we did at the very beginning of this chapter. Molar mass, remember, is grams per mole. Now, a little trick you can use with chemistry. I'm going to look at what I have and see how I can put them together to get these units. You see that my actual compound is 15 grams for 0.129 moles. Okay, so that is going to give me 15 grams, 0.129 moles. That's going to give me 116.3 grams per mole. Now I have the 2 molar masses that I need. In your assignments, I wouldn't expect you to write all these headers that I'm putting in. I'm just doing this so you know what we're doing next, but make sure you order things in a way that's easy to follow. So the multiplier ratio, remember, that's going to be your actual versus your empirical. We have our 2 molar masses up here. That's going to be 116.3 over 29.02. This is going to give us 4.008 when we divide it out, or just about 4. So that's going to be our multiplier. So we're going to take CHO. So we're going to take our empirical formula. Now it's going to be C, your subscripts are going to be 1 times 8, H, 1 times 8. Nope, not 8. Sorry, that had to be confusing. It's 4, 1 times 4. H, 1 times 4. O, 1 times 4. And our molecular formula is going to be C4, H4, O4. Okay, so that is how you work with finding empirical formulas, molecular formulas, using some experimental data to find percent compositions, and how percent compositions flow into empirical formulas that flow into molecular formulas. All right, now we're going to go on to look at chemical equations. So we've been using them. We're just going to talk about them a little bit for example, uh, chemical equations are basically showing our map from reactants to products. Your left side is your reactants. Your right side is your products. One of the things that has to happen is all of the atoms have to balance. So you have to have the same number of atoms on the left as you do on the right. You're seeing the phase called aqueous, which is dissolved in water, or it means your compound is in solution. Now, I've given you here something else to take a look at. This is a type of reaction called a double replacement. You're going to do a lot of these in your labs because you notice the double replacement is all the ions switch. So your lead that is with your nitrate, let's see. So basically, let's do it like this. Your nitrate's going to come to your potassium. Your iodine is going to come, your iodide is going to come to your lead. So here you see you have your lead iodide and your potassium nitrate. That's your double replacement. Now, in particular, this is a specific type of double replacement known as a precipitation reaction because you have a solid as a product. Make sure you're getting these standardized reactions in your head, what they look like. Double replacement means your ions are going to switch places. They're going to trade. And then let's see, we have a mixture, an aqueous solution of lead 2 nitrate with potassium iodide. We get lead 2 iodide and potassium nitrate. Well, how do I know that that's lead 2 nitrate? Well, you should be working on this. Remember, your nitrates have a -1 charge. Well, I was working on that down here. So your nitrates have a -1 charge. Okay, well, I have two of them. So that means that since one, so no subscript, so that means it's a one. One lead cancels, neutralizes two nitrates. So it has to have a charge of +2, because if you do your lead plus nitrate, you're going to get a 2 -1, which is neutral. That's how I know it's lead 2 nitrate. And again, you do this like you could do the same thing with iodide. Remember, each iodide is a -1. Uh, Potassium is a +1. It's in because it's in column 1 or group 1 on the periodic table. And again, we have nitrate at a -1. So all of these neutralize. You want to make sure you understand you're working on these names, how these ions fit together. Because remember, your ionic compounds have to have a neutral charge. So also, you say, is this balanced? Well, let's take a look. I have one lead, two iodides, two potassiums. Let's see, this two, it's going to give me two nitrogens. I have two nitrogens. And let's see, 2 times 3, that's six oxygens. And then 2 times 3, that's 6 oxygens. So yeah, every atom balances. So this is what your chemical equations need to look like. But can you balance them yourself? So here we have iron 3 oxide. Again, remember each oxide is a -2. I have 3 of them. That's a total of -6. And two irons neutralize a -6. So the irons have to yield a +6 times 2. And you ask yourself, what times 2 gives me a +6? Well, iron plus 3. So it's iron 3 oxide. Iron 3 oxide mixed with nitric acid, you need to be able to name those acids too, is going to give me iron 3 nitrate and water. Okay, let's work on balancing this. So what I'm going to do is I'm going to start and I'm just going to take account of what I have. I have 2 irons on the left. No, not 2. 1 iron on the right. On the left, I have 1 hydrogen. On the right, I have 2 hydrogens. On the left, I have 1 nitrogen. On the right, I have 3 nitrogens. And on the left, I have 6 oxygens. And on the right, I have 10 oxygens. Okay, so let's figure that out. Okay, so here, see my 3 oxygens. Here, 3 times 3, that's going to be 9 of my oxygens plus 1, 10 oxygens. Make sure you're working with those subscripts, how they work. Okay, so the first thing I'm going to do is I'm going to take a lot of your chemical equations have oxygens in them, nitrogens. You don't usually see irons, so I'm going to balance that first. So, and now keep in mind, here's a vocabulary word for you. These coefficients that I put in, the coefficients are going to be the numbers out in front that I use to multiply a molecule by. Those are called stoichiometric coefficients. So there. Okay, so I'm going to say I have iron 3 oxide plus nitric acid. And so what I'm going to do is I'm going to use a coefficient here, stoichiometric coefficient, to multiply my iron 3 nitrate and my water. Okay, so now let's count again. 2 irons on the left, 2 irons on the right, 1 hydrogen on the left, 2 hydrogens on the right. Okay, so on the left, I have 1 nitrogen. And if you have to pause the recording to count this out, make sure you're doing that. 1 nitrogen on the left. On the right, okay, so I have 3 times 1, that's 3 nitrogens, times 2, that's 6. 6 nitrogens. And then I have my 6 oxygens, so I have 3 plus 3, 6 oxygens on the left. Okay, let's look at how many I have on the right. Okay, so I have 3 times 3, that's 9, times 2, that's 18, plus 1, 19 oxygens. Okay, well, at least my irons are balanced. Okay, so the next one I want to do is I chose to balance my nitrogens. And so I have 1 on the left, 6 on the right. So that means I'm going to use a multiplier of 6. I want to try to leave my irons the way they are. I'm going to put a stoichiometric coefficient of 6 here. Okay. Still have my coefficient of 2 there. All right, now I'm going to take a moment and count again. So 2 irons on the left, 2 irons on the right, hydrogens. Okay, well, I have 6. So 6 hydrogens on the left. How many do I have on the right? I have 2. Okay, so we're not quite there with the hydrogen yet. Now I have 6 nitrogens on the left, and then I have 3 times 2, 6, 9. Okay, so those are good. Let's look at my oxygens. Okay, so my oxygens, I have 6 times 3, that's 18, plus 3, that's going to be 21 oxygens on the left. And then on the right, I have 3 times 3, which is 9, times 2 is 18, plus 1, which is 19. 19 oxygens. Okay, so I'm getting closer. Well, what's the next thing I want to do? Let's just balance the hydrogens. I have 6 on the left, 2 on the right. So if I take a stoichiometric coefficient and put it in front of water, iron oxide. And again, you see I'm trying to leave alone my coefficients. That won't always happen, but you don't just want to keep changing the same coefficients over and over again. And balancing chemical equations, it's really something you have to practice to develop a strategy. Okay, plus, and then what I'm going to do is add a coefficient of 3 waters. Now let's count again. Okay, 2 irons, 2 irons. Okay, that's good. Hydrogens this time. 6 hydrogens. 3 times 2 is 6. Okay, 6 hydrogens. 6 hydrogens. All right, so what are we going to count next? Nitrogens. 6 nitrogens. 1 times 3 is 3, times 2 is 6. So 6 nitrogens. 6 nitrogens. Let's count our oxygens. Okay, so 6 times 3 is 18, plus 3 more is 21. 21 oxygens. And then on the right, 3 times 3 is 9, times 2 is 18, plus 3 more is 21. And so our equation is balanced. So what we say is our stoichiometric coefficients, this equation we have here at our last are 1 iron oxide plus 6 nitric acids plus 2 iron nitrates plus 3 waters. That is our balanced chemical equation. So that's just a process that I go through. It's kind of a way to start. As time goes on, you can, kind of develop your own process. Just make sure you're showing some logic as you're working through them. So let's practice a balance here. Now, pay attention to the way I've written this. I'm going to use equation balancing as a way to help you practice your naming. So here you would be, so here you have liquid phosphorus pentachloride reacts with water to form phosphoric acid and hydrogen chloride gas. Write the chemical equation and then balance it. You're going to be expected to do this. Phosphorus pentachloride, ECl5, liquid, reacts with water. Liquid, do not put aqueous water. Nitric acid, well, you remember phosphoric acid comes from the phosphate ion. So you see phosphate's a -3. That means I need 3 hydrogens to neutralize it. H3, PO4, and your acids are aqueous. And then hydrogen chloride gas, HCl. See, that's why your acids are going to need to be aqueous, because see, that looks like hydrochloric acid, but it's not. It's in gaseous form, so it's hydrogen chloride gas. Okay, so let's start doing our count. One phosphorus on the left, one phosphorus on the right. Chlorines. 5 chlorines on the left, 1 chlorine on the right. Hydrogens. From the water, I have 2 hydrogens on the left. And let's see, I have 3. So 3 plus 1, 4 hydrogens on the right. And then I have from the water 1 oxygen on the left, and on the right, I have 4 oxygens from the phosphoric acid. All righty, well, let's see, what do I want to balance first? I chose chlorine. So I'm going to leave my PCl5 the way it is, because again, I have 1 phosphorus, 1 phosphorus. I'd really like to not change that if I can, if I can at all avoid that. Also, like when you have molecules with just 2 atoms in it, those are easier to change to balance others. If you ever have something in an equation like O2, always leave that to last, because I can put any number in front of that to balance out my other oxygens and so on and so forth. Okay, so I'm going to do PCl5. How much? Okay, I have plenty of room. PCl5, liquid, liquid water. Really want to leave my phosphorus alone because they are already balanced. And then what I'm going to do is I'm going to balance my chlorine by doing 5 HCl gas. All right, so let's count again. Left is 1 phosphorus, right is 1 phosphorus. Left is 5 chlorines, right is 5 chlorines. Okay, so my hydrogens, I have 2 hydrogens. Let's see, then I have 3 plus 5. That's 8 hydrogens. And my oxygens, I have 1 oxygen. Then over on the right, I have 4 oxygens. Okay, so I really want to leave my chlorines the way they are. So what I'm going to try to do is use water to balance out hydrogens and oxygens. Okay, so I have 2 hydrogens on the left, 8 on the right. So I'm going to use a coefficient of 4 and see what it does. So PCl5, liquid, plus 4 waters, going to give me phosphoric acid. 5 hydrogen chloride gas. All right, so let's count. 1 phosphorus to 1 phosphorus. That's good. Let's see, chlorides. 5 chlorides. 5 chlorides. Okay, that works. Hydrogen, 4 times 2 is 8. 8 hydrogen, 2, let's see, 3 plus 5. That's 8 hydrogens. All right. And my oxygens. Yep, I have 4 oxygens. And let's see, 4, oopsies. 4 oxygens. So that shows me that this final equation is balanced. Okay, so again, equation balancing is probably something you've done in high school, so I'm not going to go super slow through it, but just make sure you're practicing it. Realize I'm going to use these balancing equations to help you practice naming, make sure you're practicing your naming. That's going to be from now until the end of your career, you're going to need to understand chemical names. So just keep working on it. And we'll go ahead and call it for today, and I will see everyone tomorrow.